So this video is going to do one problem from page 7 and one problem from page 8 just to round out the problems that are done in the older videos. So first I'm going to do page 7, number 7, which is right here. So the value in US dollars of a piece of farm machinery depreciates according to the formula D of t equals 18,000 times 0.9 to the power of t, where t is the time in years. Now remember, depreciates is like, when equipment gets old, it's worth a lot at the beginning, but as time goes on, it just gets to be less and less and less. And most of the time that is considered an exponential curve because, like, for example, the thing is never going to be worth nothing, so it's not going to go to zero, but it will gradually approach zero, like an asymptote. So that's what makes it exponential, right? So in this particular case, I've got this equation here, 18,000 times 0.9 to the t. To find the initial cost of the machine, there's two ways to do it. One is you plug in t equals 0, because remember, the initial cost happens at the beginning, and the beginning of time is t equals 0, not t equals 1. So if I put t equals 0 in there, I get 18,000 times 0.9 to the 0 power. 0.9 to the 0 power is 1, so the initial cost is 18,000. Okay? That makes sense, right? So let's just do it with the calculator. That's an alternate way to do it in case you forget. So we'll go y equals, and we'll put the equation in there since they were nice enough to give us an equation. And then we'll put 0.9 to the t power. In this case, we're going to put x. Then we're going to look at the table. When we look at the table, we can see that at time equals 0, the value of the machine is 18,000. So that is the initial cost of the machine. Okay, so we'll write that down. So at t equals 0, the initial cost of the machine is 18,000. Next, find the value of the machine after 5 years. So this is the machine cost after 0 years. So after 5 years, we'd look in the table under 5, and it would be 10,629. So it would be 10,629. And if we wanted to, we could write here that this is time, and this is the depreciation value. So at t equals 0, it's 18,000, which is the original cost. And then after 5 years, it is 10,629. Okay? All right. Calculate the number of years it takes for the value of the machine to fall below $9,000. Okay, so we can see here that up until year 6, it's 9,565. We want to know it when it falls below 9,000. So we're going to have to go down a little bit more, and we can see that year 7, it has fallen below 9,000. So we could say that in year 7, you could say in year 6, it was 95, 65, 90. And in year 7, it fell to 86, 09, 30. So we know that the answer for a number of years it takes to fall below 7,000 would be 7 years. Okay? Let's say that somebody wanted to know the exact number of years, not 7 years, but they want to know exactly if it's 6.5, if it's 6.7. You could do that easily by doing a graph. And then, let's see. The way I recommend it is, since you know how to do intersection, I think it's best to, and like, look at this value. It's like 18,000. So you can't even see it on the grid yet. But I could adjust the zoom so that I can see it. That would be zoom fit, right? So I can see this graph, which is very, very large value. There we go. Okay. And then we would like to see, when does this graph cross the value 9,000? To do that, we could put a special function in for y2, a function which is a horizontal line at 9,000. And if we do that, we can see that the horizontal line crosses the exponential curve at a certain point. All we need to do is figure out that point. How do we find an intersection again? Second calc intersect. First curve. We only have 2 curves, so you can just hit enter, enter, enter. If you have 3 curves, then you need to select which curves, right? So it looks like it's 6.58, okay? So the time that it falls below 9,000, which would be exactly 6.58 years, okay? So that would be an exact answer, but they just said calculate the number of years, so it doesn't really sound like they want a decimal, okay? The other way you could do it is you could look at the table, and then you could just say, okay, I'm just going to increase the number of steps between 6 and 7. I know it's somewhere between 6 and 7, so I'm going to do plus, which changes the step size, and I'm going to change it to 0.01. If I do that, I can see like all the different the values for different values of 6, 0.01, 0.02, 0.03, etc. I call this the Alex Howard method after the first student that liked to do this method. So let's see. I want to see when the Y1 column becomes 9,000. Oh, there we go. 6.58, which is exactly what we got using the intersect method. But you can see that the intersect method is a little bit less trial and error, so you might like that better. Okay, so that's it for page 7, number 7. Now we're going to page 8, number 9. Okay, so looking at number 9, we have a function which is 2 to the x plus 3, and they even drew the function for us here. Okay, and since they were nice enough to give us a function, we're of course going to plug it into the calculator. And I'm going to clear my old functions here, and I'm going to put in 2 to the x arrow plus 3. Then I'm going to look at the table, and oh, remember how I changed the step size to 0.01? I don't want it to be 0.01 anymore. So I'm going to do second table set, and I'm going to change the start to 0, and I'm going to change the step size to 1, like it is at the beginning, and then I'm going to quit. Okay. Then I'm going to go back to the table. Now it's back to normal, right? Now what they're going to ask me is they want to know the coordinates of the A and the B points, okay? A has an x value of 0, so let's find out in the table what the y value is when x is 0. It's 4, okay? So we know that the value here is 4, okay? What about the value for the y that corresponds to x equals 1? Let's go back to the table. 1, 5. So it would be 5. Okay? Find the value of A and the value of B. Okay, we just did that. All right. B, write down the equation of the asymptote of the curve. Okay, so we could also do that using the calculator. The asymptote you can find just by going way up or way down. Which one are you going to go to? Well, you see how this one, for the negative values of x, it approaches an asymptote. It kind of looks like it's going to approach an asymptote right there, right? So what we're going to do is we're going to go way to the negative values. And looks like it's approaching the number 3, and indeed it is. Eventually it actually gets to 3 because the calculator is not capable of displaying numbers that are really wide in this table. So we can say that the equation of the asymptote is y equals 3, okay, because the y value here is 3, okay, and that is the asymptote. All right, okay, and I'm just going to fill in some of the points here in the table. So 0, 4 is 1 point, 1, 5 is another point, okay, and the equation of the asymptote is y equals 3. Another way you could figure out that the equation of the asymptote is y equals 3, if it's in this form here, notice that the asymptote number is the value that's added at the end. Okay, that's it for number 9, and the rest of them are done in a separate video, which is called page 7 and 8, 6, 8, 10. Thank you.